All right, so welcome back to our course, Cyber Physical Systems. And today, as I was mentioning a couple of minutes ago, we're going to start with Chapter 2 on embedded computing systems or just embedded systems. That's what we're going to be referring to throughout this chapter. And these are some of the topics that we're going to discuss in the chapter. So first we're going to start with an introduction, and a big theme of the overall chapter is going to be the heterogeneous nature of embedded systems. That's what makes embedded systems interesting, useful, and also challenging. And when we make the distinction between an embedded system and a generic computing platform, be it a server, be it a laptop, or a desktop PC or a workstation, the way you visualize that is that they all sort of serve the same very general purpose. And if you visualize it, that they all sort of look the same. You know, a laptop is a laptop, and I think that we can throw in there things like tablets as well, perhaps. But laptops, workstations, PCs, servers, they all sort of look the same. So they're not very heterogeneous in nature. When we talk about embedded system, we're going to see that the purposes that they serve, the form factors they come in are very varied. So they are heterogeneous systems. Because of that, to be successful at implementing them, we have to rely on standards. So that's going to be a very important theme throughout the chapter. Then we're going to talk about hardware architectures of embedded systems, and some on that. And also design metrics. So design metrics are important because as complexity increases, the key is going to be not so much the enabling technologies, but the methodology to use these technologies so we can execute projects, so we can execute designs and developments for the betterment of business, society, and so on. So as we go through these processes and flows that are actually being developed to address complexity, we're going to need a way to improve. And a key thing to improve something is to be able to measure it. So we're going to talk about design metrics. And then in the same spirit as chapter 1, we're going to talk about modeling, things like design verification in the specific context of embedded systems. And we're going to talk about a specific technique, the hardware-software co-design, which is so necessary for two main reasons, to address complexity so that you know about issues between hardware and software early during the design cycle, and you try to execute these projects in a timely fashion, on budget, on time. So execution is an important part. So those are some of the topics that we're going to be discussing. So again, in terms of cyber physical systems, what we're going to see is that the backbone of these complex systems, or a major pillar to develop these complex systems, are going to be embedded systems that are embedded in this physical world, so the physical part of cyber physical systems. These embedded systems are going to be the first line of design that are going to link the physical with the cyber. And we'll elaborate on that later on. So that's what we're trying to do with the chapter, is to provide that strategic foundation. So when we go on to the next chapter and talk more specifically about cyber physical systems, the design specifications of those, the recommendations for designing cyber physical systems, and we're going to talk a lot about examples and applications of cyber physical systems, we have a good view of how they come to being and how they realize through the design of embedded systems. So what are embedded systems? Again, they are special purpose systems. So when we think about general purpose computing systems, again, laptops, PCs, desktops, servers, workstations, we made the distinction of embedded systems being systems that have a special purpose. They are interfacing with some physical entity. It could be mechanical, it could be through sensors, it could be the environment. And when we say interface, it's not just on the sensing part, but also on the actuation part. So we're sensing, we're computing, we are actuating and interfacing in that fashion to the surrounding environment. It also, these systems are tailored to do predefined tasks, and because of that, because you have that ability to better draw a boundary around the functionality, better define the functionality of an embedded system, you can make design trade-offs and design optimizations that allow you to design embedded systems that are low cost, low power, high performance. If you bound the box of the functionality, then it allows you to optimize very nicely in these other 3 dimensions. Up to a point. We're not talking about hardwired type chips, although we're going to make a further distinction within embedded systems. We're going to talk about sort of the processor driven embedded system, that it allows you to do a great deal of embedded systems up to certain performance, but then at some point, if your embedded system requires higher performance, then you have to transcend to programmable logic. So we're talking then FPGAs, and those still work together with processors. So it's the addition of that programmable logic fiber that allows you to get that next level of performance. In fact, a lot of the embedded systems that are using machine learning and neural networks, a part of that system is being implemented with FPGAs, because just software driven on a microcontroller or some other type of CPU type platform would not give you the performance that is needed. So we're going to see that, for example, a lot of the systems for beamforming for 5G, how you have to calculate the phase of the beam as it's going to be deflecting, that gets calculated with FPGAs. And then, of course, it goes to the RF part or the microwave part to affect the phase, but the calculation gets done by hardware with FPGAs. So we're going to be talking about both the microcontroller type and the FPGA type of embedded system. So in that case, if you do hardwire it with an FPGA, that's the extreme of having a specific task, a specific functionality, and you may have some ability to configure it, to sort of program it to a certain extent, but compared to something where you write VHDL or you write Verilog to get the functionality versus something where you write a C program, there is a big difference in flexibility there. But there is also a big difference in performance. So if we look at embedded systems, essentially it's everything that is not a sort of a PC or a Mac, including servers, type of device. They are everywhere. So when I used to do a lot of the recruiting sessions, I used to tell the people coming that why ECE was so great is because I used to use this phrase: if you can plug it into the wall or put batteries in it, we have something to do with it. That was kind of my phrase. Okay, still true, and even more so. And the amazing thing to me is that we are not even the ones coming up with the possibilities. There are a lot of non-technical entrepreneurs, and maybe because they are kind of non-technical in nature, they're not clouded by the barriers of reality, but they push the engineering community and they dream up of all these possibilities. Can we do this? What if we did this? And people are coming with amazing things, and because the economy is such in decent shape, there is a lot of capital to be put into this new services, new products that are going to make use of what we know in the realm of system development. So they are everywhere. Like I said, the best thing to think about it is if we get some type of source of electrical energy, there is an embedded system there. There is an embedded system because you are undoubtedly controlling something, you're sensing something, and you are actuating some type of action as part of the system. And that is, in a nutshell, is the very definition of an embedded system. So another aspect of embedded system is the level of integration, of different technologies. So the pure microprocessor type of market is essentially these days what is the best balance between cost, power, and performance as measured by actual software performance. So that's what are the number of cores that we can put to balance power and performance, and what is the size of the chip at that point, and what is the price that we can make it for and make the required margin. So it's really trying to get the number of cores right, and then some underlying technology and communication fabric to make those all those cores work together. And also on the software development side, how do we map algorithms and software to this computing infrastructure? So that's kind of the name of the game in the general purpose computing. So general purpose versus embedded computing. In embedded computing, there is a lot more complexity. You're trying to optimize also for cost, power, and performance, but also there is because you're going into all these products that have, they're very heterogeneous in nature, but even heterogeneous in the nature of the business requirements of these products, you have more pressure of designing components that are lower cost. And that requires more integration. Require integration of analog, digital, these days RF. So for example, Xilinx has a very nice and very expensive product line of embedded RF Fpga processor. If you wanted to do, for example, edge processing of RF signal, they have that that type of technology. So they're integrating RF, which is may or may not be, depending on the frequency, may or not be the same silicon or semiconductor processing technology that if you were just doing digital logic for a microprocessor. So you have to be aware of that. Now, the good news is that since they can go everywhere, and they are everywhere, volume in semiconductor manufacturing drives prices down. I mean, that is because there is so much parallel processing. So if you, these days, the wafer sizes are in the order of 0.5 meter, about a bit less than 3 feet. So if you think about that, whether the wafer is 6 inches in diameter or is 50 centimeters, the steps are the same. The amount of leverage and efficiency that you get from processing this area, from processing this one, are tremendous. You get a lot more area, more chips. You have to do the same thing. You have to go and put the wafer through all the same steps. And because, so if you're doing volume, high volume, that drives the cost down. And so these chips are everywhere. A good example, and some statistics quote that any household, not including the car, any household will have more than 50 processors in it, in the household, worth of embedded systems or embedded processors. And then the car is just basically double that for each automobile. So this is a list, not a comprehensive one, of where you would encounter embedded systems and hierarchical embedded systems. For example, you can look at a car and say, well, that's a, there are embedded systems there, but the anti-lock brakes is a subsystem of that. It's going to have its own processor. It's going to connect to the one of the 3 networks that are running in the car for different things, and so on. So that's just a list of a bunch of equipment that are good examples of embedded systems. So very pervasive. So what is the key? The key to make this work? Now we know that we have a processor. Okay. And how do we make it work in this heterogeneous field of functionality and requirements? The key is peripherals. Peripherals. So many peripherals. So many peripherals. So have to do with communication. So serial communication interfaces. So your basic 2-wire, 2 to 5-wire UART, whether you're doing flow control or not, hardware flow control. So that's an asynchronous communication interface. What we call the second layer, the link layer of the protocol. It looks pretty much the same as a UART, but then at the physical layer, there are variations that are more robust, electrically resilient, and you have all these different type of standards at S232, 422, 485, and so on, whether you're just connecting something simple or just have some type of bus in an industrial environment. Then you have synchronous serial communication interfaces. So these are, at least 2 of these are widely used in embedded systems. So you have I2C. We'll talk some more about these specific interfaces. We have I2C. So that stands for integrated circuit communication bus. Then we have SPI, serial peripheral interface. So I2C is a very nice peripheral interface to sort of daisy chain and make like a board area network, if you will, on a board. So it's a serial bus, uses only 2 wires, and so basically you can hang from there any number of chips on the same board. There are actual electrical limitations. There's so much that you can hang on the bus. It's a master-slave approach where you have a single master. Although there are multi-master extensions. And then you have SPI, which is a clock and 2 data lines for input and output. And it also is a master-slave type of arrangement. Then you have things like the universal serial bus, USB, which is really becoming one of the... So there are many interfaces, but you're always trying to pare things down. And when you're going off board in a wire fashion, USB is becoming kind of the workhorse of embedded systems. If you're going to connect board to board, and the latest standard of USB supports peer-to-peer communications. It was conceived as a host device. They didn't use same idea, master-slave, but they used host device, where the device was sort of the slave in the arrangement. But more sophisticated than anything like SPI or I2C. You have hosts, you can have hubs, then you can have devices. You can essentially form like a star topology, form like a network. So you can see that inside a cabinet, if you have a system where you have multiple boards, USB is a nice bus, lets itself. And it's high speed as well. Not only you could do, it had different speeds when it was conceived, at 1 megabit per second, all the way to 12. But today you can stream video via USB. It's much higher than the original spec. So that one is a very important one. A lot of these embedded systems have right there has the USB interface integrated. And all you have to do is hook up your connector, and you can develop USB applications very, very quickly. The software of these applications normally are called the stacks, the software stacks that manages everything down from your actual application. If it's, you only know your application, but below that, there are a lot of standards, and that lends itself for reuse, not only of the hardware, but the software, and it lends itself to quick development, quick time to market, which is one of the things that you need to do to deal with complexity. Then we also have media type devices like SD cards. Compact flash, nobody uses compact flash anymore, but certainly SD cards and micro SD cards and all different form factors of the SD, which is actually an elaboration on SPI. So it's a sort of a more advanced multi-wire SPI. So that's the SD format. Then you have networks, wired networks, Ethernet, very much still slowly but surely transitioning to gigabit Ethernet. When I say Ethernet, I'm referring to the lower bandwidth, what is called the 10100 standard, but really gigabit Ethernet is the what everybody is evolving towards. And long works, that's sort of a another type of network for industrial applications. Then we have what is called field buses, which are very much used in cyber-physical systems and devices to sort of network and connect a host or a master to distributed actors throughout the system. So I'm talking off board. So the controller area network bus, the CAN bus, very much used in automotive for the middle tier, network. So this is the CAN bus has features of serial communications, but it has a lot of, at the lowest layers, it still has a lot of safety features borrowed from avionics and fly-by-wire type of systems. So your anti-lock brakes, your anything that has to do with safety in a car, your airbags, things like that are going to be on the CAN bus. Okay. Then another bus that is used as a field bus in cars is the LIN bus. So it's actually an evolution of the simple UART protocol. In fact, with software, you can implement the LIN protocol on a UART. Or it'd be better if you have the hardware. It's actually not that complex. But the LIN bus was conceived as a lower tier, lower cost, simple bus because they were using the CAN bus for the car for almost anything. But as more electronics were added to cars, we were putting too many things on that CAN bus, and the primary priority was safety. So the LIN bus was evolved to basically put in that LIN bus all the lower tier things. So the things that are going to be in the LIN bus are your mirrors, your defoggers, your things like that. That are still, each one of those are going to have a processor actuating those actors in the system. Then we have Profibus, this process field bus, widely used in processing, pharmaceutical processing, and things of that nature. We also have timer peripherals, so phase lock loops for synthesis of waveforms and frequencies. We can have capture, compare, and time processing unit peripherals. So capture allows us to be able to measure the time between events of digital signals, and compare allows us to basically output a digital signal for a predetermined event. So the compare part of the capture compare peripheral is the part that gives you the PWM signal, for example. So we have that as well. And then we have our discrete I/O, or GPIOs. We can turn them on, off. They're actually quite sophisticated these days. Not only they do 0 and 1, but they have also integrated pull-ups and pull-downs. You can do open drain configurations, which means that you can drive to higher voltages than what the chip can withstand. And you can also, of course, tri-state it. So those are your general, kind of all the functionality of those GPIO pins. And you have analog to digital and digital to analog conversion. What important. These days you're also seeing some further integration of analog. I think that the PSOC architecture does a good job of integrating a little bit more advanced analog peripherals, but a lot of other vendors are starting to do the same thing. and you can get integrated temperature sensors, band gaps, op amps, comparators, and things of that nature. So those also look like peripherals in the embedded system computing element chip. And last but not least, you have all kinds of protocols for debugging and doing board level testing. So like JTAG. So that's on the sort of hardware side, you know, the things that you're going to get on that main chip that is going to make your embedded system, but also on the software development side and the system development side to make sure that you can keep up with all this functionality. And because it's not only the rich peripheral set, is that we can do all this functionality and have all these peripherals with very low power. And also, another thing that I didn't mention is that these chips come with a lot of memory. So you can fit very large programs, both on the data side and the program side. You can fit quite a good deal of functionality, and also that you can have also non-volatile memory like EEPROM. So a lot of functionality on a single chip. So to keep up with that, being able to harness that functionality on the development tool side, there have been a lot of advances as well. So you know, we use compilers and debuggers mainly, try to minimize assembly. There is a place for that, but let's just stick with compilers and debuggers and some of the more specific tools of embedded system software development. We have the ability to serialize the code. There is a lot of functionality on these chips to protect the code, so it cannot be reverse engineered. And there are abilities in these tools to obfuscate the code. So even if somebody can look at it, it'd be at least very hard to be able to tell what is going on. So there is a technique of security and protection via obfuscation. So that's some of these tools can do that. Serialization again, maybe you need to be able to serialize each of the systems for some reason. So, and you're not going to compile a single, you're not going to compile the system each time just to program each individual or unique product. You have to have a way of serializing the product in a more efficient way. So electrical IDs is another type of peripheral that some of these chips come with. Higher up on the hierarchy of tools, system development tools like MATLAB and Simulink are coming with features where you can actually generate code that you can directly implement on an embedded computing system. That's on the works. It's a tool generated code, so it's not, you could do better if you do it, but it saves you time. And it's a first approach to see and get some feedback in the development cycle. It may be just the thing to do. And as the system matures, maybe a human can do better. But these tools, you can generate code, not only C code or C++ code, but you can also generate Verilog if you're using an Fpga type of approach. So they also, of course, include, like MATLAB, the ability to generate system from state charts or state diagrams, and again, you get the software right out of that you can implement in the embedded system, or again in a Verilog if you're going to implement in an FPGA. Another thing that you can generate graphically that is important is interrupt handling algorithms or schemes. There are two ways of doing that. You can do it at a native level. So we're talking about a system without some type of operating system. But so you can basically craft your own scheduling, your own interrupt handling and task handling approach. But the systems that we are talking about and operating systems have operating systems for embedded systems, because of their increased usage, again volume, they are coming down in price considerably. Pretty soon there's going to be no need to avoid using a real-time operating system, because the development is going to be able to afford it. It's going to be easy enough to develop with it, and you're going to have enough memory in the system that is going to be a no-brainer. Why not use an RTOS that basically handles all the scheduling and all the inter-process communication, and you focus on your application. You focus on your application. So that's kind of a bit on the evolution of the software development tools. So again, RTOS, very important, and a good example is the DSP Nano RTOS. So that's if you have DSP type applications. It's a very small, straightforward to use RTOS that you can use for DSP type signal processing type of applications. We tend to be simple when it comes to the operating of it, because you're sort of doing a very specific algorithm, and what changes is the stream of data that you have to process. So the data stream is a lot, but the actual processing on that data stream tends to be very specific, very specific. So that takes us to the paradigm of multiple data, single instruction type paradigm of computing. So if you are developing software, people can develop their own tools, vendors, keeping in mind that the vendors of hardware, what they want to do is sell hardware. Any type of development on tools, although they can be very good, are really a collateral to be able, or to enable people to develop for their tools. I mean, for their hardware that they are commercializing. So some vendors, they generate their own hardware. A lot of tools start with the GNU software suite. They have a lot of different software tools almost for anything. And a lot of software tools, you can see that they are repackaged. They are repackaged GNU software. And then that allows us to use a lot of the kernels that are available through GNU, but also on the overall IDE side, the NetBeans platform is being used. That's also an open source platform that a lot of vendors get, and they repackage to get a head start in putting these tools together, because it's a tremendous investment. And that's not their core competency. That's not their core business. They're there to sell chips, not to sell tools. In fact, most of the tools you get for free. So things like tools that where you can develop with Linux or Java are popular based on the NetBeans platform. So part of being able to implement complex systems is going to be the ability to operate these tools. because that's what's going to give you the productivity and the efficiency to put the systems together. So like anything, you're as good as how well you use the tools that you have available to you. So, and as much as they try to make it easy, the tools are, because they do a lot, the tools are complex. And in a sense, they want to strike a balance of how easy it is to implement with their product, but also how much they can also get you used to their tools so you remain a customer. That is it's an interesting balance. So the tools are important at these two levels: software development and system, and then when you actually are implementing the system, after you write the code, the ability to debug and the system, the ability to get visibility into the system and be able to perform that important part, which is debugging your system as you implement it. So the penetration of software development as part of the hardware development cycle, and as we are defining and implementing these complex systems where hardware and software are two equal pillars of this embedded system, which is a pillar of the complex cyber-physical system, requires a strong methodology of hardware-software partitioning, and later we also want to talk about co-design methods. So that's how you deal with complexity and how heterogeneous these systems are. And I want to talk in terms of a system that has everything. It has software, it has synthesized hardware in the form of, let's say, an FPGA, programmable logic fabric, and it also has a processor where you write software for that part of the system. So you have the three parts. You have the core, say an ARM core on a sea of embedded in a sea of programmable logic in an FPGA, and that is the start of your embedded system. You can have more things outside of it, but you have the software, the core, and the programmable logic. That paradigm of being able to manage Verilog and C both as part of the same system, and also knowing enough about all the peripherals and all the functionality of the core that is embedded, that is a system that we're talking about. And then being able to interface that system where you are developing for the specific chip with an upstream system like MATLAB or Simulink where you develop your algorithm. So instead of going through serial steps, you synthesize, and you validate that, and then you integrate, and you go back and change it. We want to be able to look at everything at the same time. So co-synthesize the hardware and the software so we get rapid feedback, and that type of feedback allows us, that methodology allows us to do the best in terms of hardware-software partitioning. It's not always clear what should be done in software and what should be done in hardware. And at best, when people think about it, the approach is ad hoc. A lot of time is based on what's available. But if I have two software guys in the team and one hardware, but maybe we try to do as much in software as possible because we don't have that much of a hardware expertise, or vice versa. But if you want to be able to accurately design good complex systems, you have to have a methodology. You have to have a methodology to be able to quantify and try to, in some sense, optimize what is the best hardware, software partitioning as one of the first steps in your architecture design. And to be able to do that, you have to be able to measure it and get that feedback. Like I said, there is not an equation that I can give you. Say, this is the, and take the derivative and set it to 0, and that's the optimal. No, that doesn't work. It is an iterative process, and to go through iterative processes that efficiently, you have to get that feedback quickly. So if you look at, for example, the Xilinx tools that you're aware of, there are chips that have microcontrollers, and of course you have the FPGA part of, but they're embedded in the FPGA fabric. But right there, in the Xilinx tool, you have your code, you have your compiler, and you have your Verilog or your VHDL, and you are, and you can link that to MATLAB as well. And through that cycle, you can start with your algorithm in MATLAB. You can export that, both the C and the Verilog, to Xilinx. You can start doing your compilation and your synthesis in Xilinx and start getting feedback as you simulate, or perhaps as you, if you have an evaluation board, as you download the code and the actual bit stream and you actually get some hardware feedback. You can do that very quickly. And it's amazing the complexity that you can generate in a very reasonable amount of time. So those are the systems and the methodologies that we want to be able to use to be able to implement and realize these complex systems. Hardware software partitioning that is quantitative, that is driven by design constraints, and hardware software co-design, so we can get that feedback and get to the best partition and architecture of the system. So just to reiterate what I said, when you have processes-driven co-synthesis, which is really the outcome of good hardware software partitioning, and then you have co-simulation of the hardware and the software. And when we say co-simulation, it doesn't need to be necessarily in your computer. It's not necessarily a software type of simulation. If you put it onto an evaluation platform, you're still doing simulation because it's still not your system. You're still doing simulation because it's still not your system. It's just that the evaluation hardware is running in real time, so you can view that as an accelerating, an enabling platform of your simulation methodology, but it looks no different from a methodology perspective. So that part we can and we should try to standardize, and we should try to turn into a methodology, a discipline methodology as much as we can. Because part of the system level validation, system level test, that's what's unique about your application. That you cannot reuse anything. If you're developing a new system, the actual validation and test of your system is very much tied to the feature set of your system. In fact, high level test platforms for your system are unique, are customs to your system, and they are as much work to develop than the system itself. So you really need to be thinking about two systems. When you are developing a complex system, you are developing the system, but you also need to be thinking about the system to test it when you actually start manufacturing it. That's another system that is complementary, and because of that complementary nature, and from a functionality perspective, that symmetric nature is going to be as much work as the system itself, what you're going to use on the other side to test it. That part is unique. So what are the potential results from what we call co-methods? So co-synthesis, co-simulation, co-verification, co-design in general. We're able to work at a higher level of abstraction because that higher level of abstraction is the specific functionality of your system. You don't need to worry about how some type of a standard operation gets done. And when I say operation, I use the word very broadly. It's not a micro operation, but it could be a sizable operation, but it's still a standard operation. You don't need to worry about that. That may be offered, that is part of the library. It's part of the library. In a sense, you cannot always start from zero and hope to achieve high quality, high complexity, and a reasonable time. So reuse methodologies become very important. So you can deal with this complex systems and comprehensive applications. Again, in a short time to market, and being able to leverage different technology platforms according to what you're trying to achieve from a system level perspective and from an execution level perspective in terms of the budget that you have, the time that you have, and the tools that are available. So Fpga versus an Asic, which is an application-specific integrated circuit, or one of the great things that we're doing now is we're putting multiple chips inside a package platform. So the same type of, because the die are so small, the same type of packages where there was a single die inside, single semiconductor die inside, now we have multiple of them, okay? That's system in a package and is allowing more integration of functionality per actual size of real estate. So why don't we make a big chip? Because remember that the yield, because of the intrinsic defects on, let's say, silicon, if that's the technology and the process that you are using, there's nothing you can do about the intrinsic defects in the material. So you get, percentage-wise, is directly related to the size. So you get better yield with smaller chips, in fact. So you want actually to make chips that are smaller, and now if I can put all these smaller chips all together inside a single package, that gives me a lot of lower cost and more functionality integration. Because if I have a big die, it just takes one defect in this corner and it's random. It just takes one defect in this corner, the whole die is bad now. I wasted a lot of, but if I make the die smaller, the probability of that defect landing in my smaller die is smaller. So there is a higher probability of the die being good, just from intrinsic defects. There's nothing we can do about that. Those are anomalies in the lattice of the material. So system in a package is something that there are a couple of new companies really making an effort to making it pervasive, essentially. But I do think that it's going to give us that next bump of functionality at a lower cost that are needed for these complex systems that we are discussing in the context of cyber-physical systems. All right. So what are some of the advantages of these co-design methodologies? Obviously, we want to design at the highest level possible of abstraction and be able to, you all have some experience with being able to design with an RTL, be it VHDL or Verilog, always trying to design at the highest level of abstraction possible, and also being able to reuse and integrate well-known blocks at some level. If you're going to be mapping something to an FPGA, obviously you don't know some of the physical aspects of that implementation because you're going to map it to a new FPGA, maybe combine a block that somebody else designed and adding it to your design, synthesizing the whole thing together and coming up with a new design. But the fact that you can reuse a block, that's important. So trying to design and at the highest level of abstraction and reuse as much as possible. In the sense of that hardware, we try to work at the highest level of abstraction possible and reuse blocks. The same thing is applicable to software development. So we can also reuse and design software at a higher level of abstraction. So that as all the systems become more complex, and if we use the paradigm of standardization, that opens a lot of opportunities for new business models. Not that they are not used now, there is a strong and healthy amount of intellectual property type of business that people, that's what they provide as a service or as something tangible via some type of encrypted netlist or RTL or a library in software. There is a healthy business of that, but that is going to increase. That is going to increase. The ability of you being able to start a business by providing pieces of hardware and software that other people can use to implement their complex systems. That's going to increase. Some of the IP may be not soft, but not hard, but like sort of firm. You can reconfigure the intellectual property so that other people reuse it. So all this is possible because of how much more less expensive we can manufacture this semiconductor chips. Another part and another opportunity for these methods is the idea of how to test the system. Because as complexity grows, ad hoc methods of testing actually reach a plateau. And that is not because you throw more patterns to the system, you can actually actuate all the different paths of functionality that the system may encounter eventually. So you need structured methods of testing, not only in hardware, which a great deal of very interesting methods exist for hardware, like a scan design, BIST, built-in self-test, but in software. In software, of course, latent defects and bugs, or latent bugs, not defects, to make a distinction from something that is intrinsic versus something that is human caused. So a bug that is caused by the implementer in hardware is much more disastrous than in software at least from a time perspective. You have to then, it's something physical. You have to fix it. But they are not any less dangerous if they are in software. Software can have dire consequences as well. So now we need to come up with structured methods to test software so that we can try to exercise all the different functional pathways that the system is eventually going to encounter. That's a challenge. That's a challenge because if we don't do that, then we encounter latent bugs. The paradigm of having periods of alpha and beta testing, well, that's a good paradigm, but now you are introducing that in the critical path of your development. You have to wait that in some type of organic way, you wait for the alpha and beta periods to flesh out those bugs, because there is not a structured way. So I think that the software development methodologies are going to, I think, and there is a lot of research on that, learn from the hardware, because that's where the focus was, because of the consequences that you have to do something again physical. But I think there is a lot to learn from the hardware structured testing techniques that can be put into the software development. So part of the systems, again, is not some, I think a theme that I'm trying to use throughout is that we're not talking about some hardware-centric system with, by the way, some software in there, or even vice versa. It's not a very specific or genetic hardware, although it could be high performance. But that's like what a PC is. It's a very specific genetic hardware with a myriad of software around it that you can do anything with. That's the other extreme. We're not saying that either. We are talking about that because of the complexity necessary. They're both equal. Equally important, equally heterogeneous, equally complex. And that's what makes the system what we're going to be calling a systems of systems, because you have this hardware complexity and software complexity. So, embedded systems, 95% of processors in the world are in embedded systems. We think that we know that, and it's just going to increase as these cyber physical systems that we're discussing in this course. It combines that computational power with the physical interface, the physical system. And in the next chapter, we're going to go through a lot of different opportunities and examples of designs of cyber physical systems, in which a lot of them are an evolutionary step from systems that already exist, but it's making those systems smarter, better, and through the management of complexity. So some of the things that we're going to be talking about in the next chapter are smarter automotive and overall traffic and mobility systems, smarter technology for energy management, delivery, a lot of also medicine, healthcare, that's a big area, and manufacturing, smart manufacturing. So these are kind of the 4 of the top domains and applications where the most opportunities are for these complex cyber physical systems. Which make use of technologies, not only sensors and nodes of sensors, but also RFID technology. We have a big chunk later on, beyond chapter 3, a big chunk of the course on RFID, and it's fascinating to me. It's been used for a while, but it's one of those that we have not seen the boom yet. Okay, because it has to do with a lot of the usage of that technology has to do with asset and identification and identity. Those are things that people hold very dear, the asset, protection and tracking and identification. So, but as we can develop more resilient and higher quality systems, at some point people are going to say, yes, it's okay that you don't have anybody in the store and people just come in, they put everything in the cart and everything is RFID, and they just walk out, it gets scanned and charged to their credit card, and we don't need to make a line at Walmart. So the business community is not comfortable with that. That's what's taking longer. Other technologies, in the media side, there is, I think, less at stake. So if you compare two technologies, sort of like Bluetooth and RFID, the boom of Bluetooth being much more. Why? Because, okay, the application is, listening to your music or controlling something, so there is a lot less at stake. But RFID technology is one of the key technologies to this overall Internet of Things opportunities and paradigm. So we'll talk a lot about that, and that's why I kind of singled it out there. So the challenge of this cyber physical systems is not the union. It's not everything that is embedded systems and everything that is physical system. Now just throw it together there, and that's what it is. No, it's not the union, it's the interception. The interception, how can I make best use of smart computing paradigms to get better access, better control, better interusability with the physical world in a very abstract manner. Everything is physical. So you have these systems of systems where all these devices are going to be talking to each other, communicating with each other through some type of communication interface. Could be web services to collect data. How do you partition in a system that is very heterogeneous? You have your embedded system at the edge with a physical world or plant, but it's also networked, and you also have the cloud. How do you come up with a methodology? Or rather, we need to have a methodology to be able to optimize where the computation happens. Does it have to happen at the edge? Maybe, but how do you know? Maybe it's better, or maybe it's more expensive, or maybe you have time to send data to the cloud and then the result can come back. And so that trade-off of partitioning at the hardware level where things happen, which also has an implication at the software level, the methodology to come up with that partitioning at that co-design is going to be very important to be able to achieve this complex systems, because the idea is that everything is interconnected. And in terms of bandwidth, that's the big promise of 5G. That's the big promise of 5G. So, as an example, the next picture we have some type of an embedded cyber-physical system that has three parts. So we have a plant that is a physical part, and it could be a process. So I want you to be able to think very abstractly and open about this. This plant may be a process, maybe it could be a very classic type of electromechanical machine, or it could be a process that is distributed. It could be anything. But the point is that you cannot have everything at a single point. There is some distribution of the embedded system and the control for that plant through some type of network fabric, because it's not monolithic. It's not monolithic. That's the key. Okay? So we have this network fabric that is part of the system, and now we have to take into account in our system design, because a network fabric is not a connection. There are other things that we have to worry about when we go through the idea of a network fabric. We have to talk about latencies and different, how we model response time. Things are things are different. So we have something like this, where we have, again, this physical plant, and this could be something more classic, like a machine or a set of machines, or it could be something that more heterogeneous. The point is that because of the nature of this physical plant, the point is that sensor 1 and 2 cannot be connected. Cannot be connected in the classic sense that I can just run a wire from one to the other, or have it on the same board. So this physical system now has to be controlled. Part of this control system is two platforms that each one is an embedded system. And these two embedded systems are connected by a network fabric. So imagine, and it doesn't have to be a big plant, but imagine some type of safety device in what it would be a body area network, where the sensor for some reason could not be tied to the a single embedded system. You may have to have, if this is a safety device that is making is protecting you or doing something, but is sensing somewhere else in your body and the protection is somewhere else. Okay? So maybe the network fabric is maybe a Bluetooth network connection. And you're sensing something in one part of your body that is not connected, but you are making an actuation somewhere else. So the sensor and the actuator are not connected monolithically. So you have to go, that is a complex cytophysical system in a very small space of a body area network. But that doesn't make it less complex. So that's the kind of idea that we have here. We have two platforms, one in one section, one in the other. And you may have a sensor and some computation in platform number one, and that output goes to some computation in platform number two, which is using data from this physical interface point that goes to sensor one here and sensor two here with some computation. And this may be the merging of what is called sensor fusion algorithms, and that may dictate what actuator one does through this physical interface. Then another output of this computational block can go back in here through the network fabric and also be part of computation one. So you can see the closed loop in there. So how to model this type of system, taking into account things like network fabric latencies and characteristics of the network, is a different paradigm. Because we're no longer talking about, this is just a board that we're building. So we're talking about a distributed system with multiple access and points of interfacing with the physical world that we need to start and be able to model accurately so we can develop later and with the least risk of execution faltering. So we're going to stop here, and I'll see you on Wednesday.